Our daily intake of calcium is highly variable, but our calcium concentration is very, very stable. Why? Because we have a regulatory system. We have a homeostatic system that keeps our calcium in a very narrow range. The reason for that, I think by now, is probably quite obvious to you all. Because calcium is involved in so many rapid reactions that involve calcium movement down the concentration gradient, well, the body has to keep the calcium level solid and stable so that concentration gradient is stable and solid, right? So it's all about maintaining the concentration gradient of calcium. It enters cells quickly and does its thing. All right. So our normal extracellular fluid calcium concentration, it's about 2.4 milliequivalents per liter. Now, remember, you don't have to memorize normals yet, okay? So I would give you that in an exam if I wanted you to tell me if it was high or low. Calcium has a number of forms, all right? And the total amount of calcium in the blood is actually relatively small, all right? The amount of calcium that is biologically active in the blood is smaller still, okay? And that's because of the ionized binding. So half of the calcium in the blood is in the Ca++ form. The rest of it is bound to plasma proteins, right? Remember that proteins tend to have regions of negative charge, right? Regions of negative charge are going to tend to bind cations. Calcium is a cation, so it ends up bound to that. What's happening?
I was getting a phone
Oh.
call. My backpack was vibrating.
What's going off? Okay. So our intake has to be balanced with output. Most of our output is through the GI tract. In other words, there usually is an output. In other words, usually our amount of calcium in our diet is greater than our calcium needs are, right? So it means there's excess. There's calcium to leave the GI tract in the end. So about 900 milligrams of the 1,000 milligrams we take in just goes right on through, right? So in other words, we're absorbing a relatively small amount. Now, interestingly, when we are calcium deficient, this can change quite dramatically. Under the influence of vitamin D, the GI tract can dramatically increase how well it reabsorbs calcium. So like this 10% absorption here can go up to 30 or 40% if the body's calcium level is low. Now, just like potassium, most calcium in the body is still in the ICF. Now, that doesn't mean the calcium concentration in the ICF is higher than the ECF. That's not what I'm saying. I'm saying total mass, total grams of calcium, most calcium in the body is still in the intracellular fluid. All right, so, 0.1% of the calcium is found in the ECF, 1% in the ICF, so we're up to 1.1%. Where's the rest? Locked away in bone, right? The bone calcium is crystallized, so it doesn't directly participate in the calcium concentration of the blood. Now, the important thing, though, is the calcium locked up in bone, it's the same, calcium is calcium, right? So the fact that our bones are made of calcium is because that makes them strong. But the body uses the fact that we have a storage form of calcium to keep our calcium concentration level. Short version is this: the body will steal calcium from the bones to maintain a plasma concentration. Okay, so if you take calcium out of your diet, bad idea, right? But if you were to do that, your bones, where would your body get calcium? It would steal it from the bones for as long as it could. Because what it won't do is let you have a calcium concentration that's too high or too low. Okay, so that is one of the weirder bits of calcium. We have an intake and an output, but then we also have a storage form where we can add calcium to the bones or we can take calcium out of the bones. So we have sort of a third part of this system. So the major players here, parathyroid hormone, vitamin D, are the two major players. The last player we're not going to really talk about until our endocrine system, and that's calcitonin. Okay, calcitonin works in opposition to parathyroid hormone. All right, so let's look at the basics. So if we have a decrease in plasma calcium concentration, the detected response is at the parathyroid glands, which are in the parathyroid or near the thyroid gland. They sit at the back of the thyroid gland. There's 4 parathyroid glands. When calcium is low, parathyroid hormone is released. It has several key effects. 1, increased calcium release from bones. We call this osteolysis, okay? And it's accomplished by osteoclasts. Osteoclasts eat away bone and release calcium and its sister, phosphate, right? Bones are made of calcium and phosphate. You can't release one without releasing the other. So that's first. That's going to tend to elevate our calcium concentration. Parathyroid hormone increases calcium reabsorption at the kidney. Not surprisingly, distal convoluted tubule effect, all right? And then parathyroid hormone increases the activation of vitamin D3, and vitamin D3 then dramatically increases the amount of calcium absorption from the gut, right? So our calcium intake is optimized, our calcium loss is reduced, and we steal calcium from the bones. All right, so all of those things are going to have a tendency to elevate the calcium concentration and fix the original problem, okay? So in the proximal convoluted tubule, we have, not surprisingly, obligate reabsorption of calcium. Calcium is a teeny tiny little ion. It's positively charged, so it's freely filtered, right? It can be freely filtered at the glomerulus, but then very rapidly 80% of it will be reabsorbed here. And the reabsorption of calcium at the proximal convoluted tubule is mostly paracellular, right? So it's going between the cells through those the looser junctions that we find there. So that's the 80%. You'll notice that we don't really have a lot of fancy machinery here, right? Proximal tubular cells, here's our lumen, here's our basolateral. We do have a calcium pump. That's going to favor calcium reabsorption pretty strongly. And then we also have a sodium-calcium exchanger that's going to do the same. So we're going to have a tendency to translocate calcium from the lumen into the blood, i.e. reabsorption, right? So 80% is through the paracellular, 20% is through the transcellular. So through this calcium channel, I was trying to see if I named it. I didn't name the particular calcium channel, but the 3Na1 calcium countertransporter and the calcium pump ATPase, right? Both of those are going to tend to lower the concentration inside and favor reabsorption, right? Favor from lumen into blood. Now, there's also significant reabsorption in the loops of Henle and in the distal convoluted tubule. Here it is mostly transcellular. That shouldn't surprise you. Remember, these are sites of regulated reabsorption, and paracellular reabsorption can't be regulated. How could it be, right? Because we have this space. The transcellular can be regulated because we can turn down the pumps and channels involved, right? So 50% stimulated by parathyroid hormone. Parathyroid hormone does stimulate these two transporters. And then half is still paracellular. Last caveat is parathyroid hormone and vitamin D also stimulate reabsorption of calcium in the distal convoluted tubule and nephron loop, right? So I kind of have repeated myself there. Oh, what I'm saying is PTH and vitamin D stimulate this third bullet point, right? The active transport. Okay, so if we look at what makes it go up and what makes it go down, okay, what decreases calcium excretion? Increased parathyroid hormone, right? Remember, parathyroid hormone is released when calcium is low. So it makes sense that if our calcium is low, we want to block excretion, right? So we're going to increase reabsorption. Now, it also, parathyroid hormone increases phosphate excretion by decreasing its reabsorption. Calcium and phosphate have to go opposite each other, okay? If we're going to steal calcium from the bones, we're going to get calcium and phosphate. The calcium we want to keep, the phosphate we want to dump, right? So parathyroid hormone, which triggers the release of both from bone, it causes the reduction in calcium excretion, but the increase in phosphate excretion. So we get rid of the phosphate and we hold on to the calcium. Decreased extracellular fluid, decreased blood pressure, increased plasma phosphate, metabolic alkalosis, and vitamin D3 all decrease calcium excretion. The opposites are true for increasing calcium excretion, right? So if our ECF volume is high, if our blood pressure is high, if our plasma phosphate is low, all of those things increase calcium excretion. So one of the things that's interesting here, you'll notice that if your plasma phosphate concentration is too low, all right, that is going to tend to increase your calcium excretion. In other words, if you don't have enough phosphate in your diet, you're not going to have enough calcium circulating because you're going to tend to dump it, right? So it's one of those weird things. Now, none of us have to worry about that because there's plenty of phosphate in our diet, right? Because remember, phosphate is one of the common intracellular buffers, all right? It's also the P in ATP, right? So there's plenty of phosphate around. And then metabolic acidosis. We're going to talk about acid-base balance today. So you can see there's a relationship between calcium excretion and metabolic acidosis and alkalosis.